We're up to x86 disassembly. This is a very important skill, quite esoteric and mathematical, and you can get a lot of money if you get good at this. Most people are terrified of it because they got traumatized by algebra at an early age and never wanted to look at a thing like this again. And that means the people that master it are in great demand. The point here, we talked about the general structure of the course. Basic static analysis looks at malware without running it in a very superficial way by just looking at the strings or the MD5 hash or something, so you do not bother to understand it in any detail. Then basic dynamic analysis runs the malware to watch it do rotten things to a machine. Again, very easy to do, but not a very deep analysis and pretty easy to fix and trick. The malware can notice it's in a virtual machine or otherwise notice it doesn't want to show you its real nasty behavior and instead do nice behavior. One example coming up in the book is there's a lot of Russian malware that will not infect Russian machines. It checks the language of the machine and decides whether to infect it or not because I don't know if this is an official policy or not, but it certainly is in fact the truth that in Russia they encourage hackers, Putin protects them. You're perfectly considered valid businessmen and encouraged as long as you don't hack people in Russia. So a lot of Russian hackers take great pains not to hack people in Russia. But anyway, that's the thing. Malware often targets one group and you have to modify it to get it to actually see its nasty stuff. So one way to do this is disassembling it. So you have to understand the levels of abstraction. The person writing a program typically writes in a high-level language like C or Java or something, and then they compile it into machine code and they strip out the symbols. So you no longer have the source code or the names of the variables or the names of the routines. This is now pretty dense, impenetrable stuff, like just a bunch of hexadecimal numbers. Now, by using a disassembler like IDA Pro, you can change it from this hexadecimal form into this slightly readable form, like push and pop and move and jump, which is assembly code, and that's as far as you can go. There's no way to get back to the original source code, although smart disassemblers like HOPA and IDA, if you pay the money for the professional version, will make pseudocode out of it that attempts to look like C, that is a whole lot easier to read. So here's some levels of abstraction. In the hardware itself, it's just got ones and zeros, which you can express as hexadecimal numbers, and those pass through the hardware chips, which combine them with AND and OR and not AND and XOR gates just to flip the bits around, and that's what the processor does. It's just take a pattern of bits and combine it to put out another pattern of bits. And that is built in the hardware. Now there's microcode, which is firmware, designed for specific hardware for things like routers and such, and this is not usually important for malware analysis, although with the Internet of Things, there is an increasing interest in malware on embedded devices. And certainly there's a whole hacking genre, hacking embedded devices by pulling out the firmware, analyzing it, and putting up other firmware to get it to do things. And I know Travis Goodspeed is one of the leaders here. One of the things he can do is he can really find out all the data on a hard drive. A modern hard drive, a 1 terabyte or bigger, is designed with extra space, like maybe 5% extra space, and as blocks fail, it silently replaces them with the extra blocks, so your hard drive appears to still have all of its blocks undamaged. And that means if you do a forensic erase of a 1 terabyte hard drive, overwrite the whole thing with zeros, you do not get all the data. There is data left over in blocks that have been marked bad. And even though they have been marked bad, that doesn't mean no data can be retrieved from them. It means there's a possibility that 1 bit or 2 might be dropped. And he told me in private communication that he was able to retrieve, I think, 50 megabytes of good data from a 1 terabyte hard drive that had been forensically erased. So you can only do that by shutting down the firmware and putting up modified firmware, because the manufacturer's firmware does not offer you any way to read the real contents of the drive, just the virtual contents of the drive. And that's fairly common. That was pretty common back when I started back in the 80s with Commodore floppies. You could trick them into writing to the blocks they weren't supposed to write to and reading from the blocks they weren't supposed to read to, and that was a good place to hide things like the copy protection. Anyway, what's that?
What about low-level formatting? Would it delete the?
I've never, I've heard all my life of this thing called low-level formatting. As far as I can tell, it's a myth.
Oh.
If anybody finds, I remember there's a Windows command that was supposed to do it. It totally doesn't work. People say this. There is a thing called forensic erasing, which writes data on the whole drive. But I'm not aware of any formatting command that actually erases the data. Certainly nothing in Windows. There's a lot of blogs that say you do a low-level format, let's get rid of it, and do a format / something. And I tried them and didn't erase anything. So I don't know. But the only thing that really gets rid of data is writing on it, and it only works if you can really write on all the physical sectors that contain data. And that only works if your computer can actually see the whole drive, and that's not true of modern drives. The computer just sees a virtual image of the drive and is not aware that block 10,000 is not really block 10,000. So what you have to do if you want to erase it, there are two procedures. One is to rely on the manufacturer's erase command in the firmware, which you can run, and you have no way to verify if it works. And from my friends in data recovery, they say it frequently does not work. And the other thing is to just physically grind up the drive with a wood chipper, and that is what everyone recommends. They say, you don't do that, you'll never be sure you really got that data off of there, because none of these procedures are good for doing it and then verifying that it really got done. Anyway,
So formatting
yeah.
is not.
Formatting never does anything. Format something, all that does is mark all the sectors available. It doesn't erase any data. You can totally retrieve the data from a formatted volume. This is a common myth. Forensic tools can just totally recover all the data from a formatted drive. It's just like throwing things in the recycle bin and emptying it. It doesn't erase anything except the file name, but the blocks of data are still there, because it would just be a waste of time to erase the data in a magnetic hard drive. Now in an SSD, it usually does erase the data because of the way SSDs are designed. Once you delete a sector and make it available, there's a garbage collection routine that will actually erase it before too long. But on a magnetic hard drive, there's no such thing, because it would just be a waste of electricity and time, because the rewrite operation can just write on top it without erasing it first. So there's no reason to bother erasing it first from the viewpoint of the manufacturer, who is only thinking about making the drive fast and efficient, and they really don't care about latent data on the drive. That's not their issue. The latent data is a side effect of the most efficient way to design hard drive firmware. Anyway, then there's machine code. That's the stuff I showed here. This is the binary data, patterns that go into the processor, and this is what happens when you compile things. It gets down to opcodes. So low-level languages, like assembly language, make it slightly easier for a human to read those hexadecimal codes. Push and pop. I must say, I used to program this stuff by hand in 8-bit processors, and I got to where I'd memorized the common opcodes like A9 and stuff, and I could actually read the hex just as well as the assembler. It wasn't that much better. But anyway, you get used to it. And so you got to learn how to read assembler to some extent. This is the most high-level language that you can recover reliably from malware, although there are some attempts to make pseudocode, but they're pretty unreliable. So most people program, of course, in things like C and C++ to make their life easier. C and C++ are the closest to assembler, so they require the most technical knowledge to program, and that's why there are so many security problems when you make mistakes in C and C++, because it doesn't contain any safety features, but it creates very fast assembly code. If you really understand C, you end up with code that's almost as fast as if you just wrote the assembly yourself, and a whole lot easier to write. And then, at the highest level, there are interpreted languages, like the Bash command line and Python, which can be, these are languages that are typically not compiled at all. Each line is processed one by one. So they typically run 100 times slower than a compiled language, but you can control their flow more easily, and this is often translated into bytecode and intermediate representation like Java. So the bytecode is then put in a Java virtual machine, and the reason people use Java, which is appallingly buggy and hard to use, is because you write one program and you can run it on any operating system, because your Linux, your Mac, and your PC all have a Java virtual machine which runs it, and so it's not as fast as C code would have been, but it's portable, which is a huge advantage. Of course, for developers, you don't have to write 3 versions of everything. So that's another layer of abstraction to consider. So what we're doing here is reverse engineering. Reverse engineering is a big, complex field, but this is the beginning of it. So you get some malware, a binary virus or malware that infects your machine, and all you have is the malware. So that's at the machine code level. You get a disassembler to turn it into assembly language, typically IDA Pro, and now you try and read the assembly language to figure out what it's doing. There are different assembly languages for each type of processor. They have different fundamental instructions. x86 and x64 are quite similar, the main difference being the registers have a different name and a different size, of course, because of the difference between 32-bit and 64-bit. But things like ARM are just very different, and all these different processors, they each have their own set of assembly codes. They all accomplish the same thing, but they're different, and you have to learn how to read them. All right, in the Hacking Mobile Devices class, we're going to be going through ARM code, because we're going to be taking apart iOS apps with IDA Pro. And that's a new thing this semester. Anyway, so I got a few iClicker questions. If you don't have one, come and grab one. I'll get my app going. Yes, all right, there it goes, good. Well, now that everybody's here, I hope you knew you were supposed to do your quiz before class. If anybody forgot, talk to me later. The quizzes are online, and hopefully you did them. If not, let me know and I'll work out some way to deal with it. All right. Okay, so what kind of language is that right there? All right, looks like I can wait till 30. All right, that is machine code. Obviously, only a machine is going to make sense of that. That's just raw binary expressed as hexadecimal to make it slightly easier for a human to read than just ones and zeros, but still not meaningful to most humans. All right. What kind of language is C? All right, I'll quit at 25. All right, it's a high-level language intended for human convenience. All right. How about assembly language? What's that? Quit at 25. All right, that's a low-level language with push and pop and jump and move and those instructions that do very little. And it takes quite a few of them to add up to something that's easy to understand. All right, how about bash shell scripting? I'll quit at 25. All right, and that's at the level of an interpreted language. Each command is processed one by one. It is not compiled into some code that's then run. It translates each command into something it can run one at a time. So, x86, this is very close to the actual physical hardware, of course, and that's what determines the language we're going to use here. So the CPU executes instructions. It's got registers on the chip, which are used for temporary storage of data. It's got an arithmetic logic unit that does things like addition and subtraction and XOR and such. And it has a control unit which determines which instruction is going to be processed next. And it fetches instructions from RAM, passes them on the ALU to be executed, and then moves to the next instruction in RAM. And the CPU can then send it out to the input-output devices if appropriate, or more often just to the memory. So that's the control unit that uses the instruction pointer, which is one of the registers, and that determines which instruction is going to be processed next. The registers are much faster than RAM. A fundamental problem with computers is over and over again you have a fast component connected to a slow component, and you have to figure out some way to avoid wasting a lot of time. So the processor is typically running 3 gigahertz or something, so it only takes 1/3 of a nanosecond to do the next instruction, but RAM typically takes 80 nanoseconds to remember something or to retrieve something, and on it goes even until you have like the human typing, which might take a few seconds to press a key, and all that time the processor had enough time to do a billion things while it was waiting for you to move. And the network card, all these things are impossibly slower than the processor, so you have a multi-threaded operating system where everything moves if it can, and if it's waiting for something, it lets some other part of the program move as much as possible to try to avoid wasting so much of the processor's time as it waits for all these unthinkably slow devices to get around to noticing what they're supposed to be doing. So the main memory is just a big pile of stuff here going from 0 to 4 gigabytes or whatever you've got. And as we've been through, you have segments here, especially Windows code. You've got data someplace, you've got the code someplace. Then you have the stack and the heap. The stack is the special memory structure designed for calling subroutines with the last in, first out process where you push a stack frame on top, and then every time you call another subroutine, you push another frame on top so you can pop them in reverse order as you return from many layers deep in subroutines. The heap is just an unstructured area where you can put blocks of memory as big as required for temporary storage, and then you can release them, and it will attempt to patch together over the gaps, accumulating empty space for future use. And we'll be doing heap exploits in the 127 class because it's pretty easy to trick the heap into making mistakes when it tries to stitch together the leftover spaces after deleting a chunk in the middle, and that's how you end up with an arbitrary write you can use to take over the processing. So data sits in RAM. There's static data that doesn't change while this program is running, and you can also call these global constants that are used by any part of the program. And there's also other data that can vary. The code is the machine language instructions, which can be disassembled into assembly language instructions. Like I say, the heap is data that changes frequently during code execution. So if you have a network card and you want to read some bytes from a network and stick them in memory until you have enough of them to figure out what they mean, you'd allocate space on the heap, put the network card in there, go do something else, and then when it's in there, come back down and look at it and do something like reconstruct an image to show it to the web browser or whatever you're doing. The stack is local variables and parameters for each function, and with a stack frame stores all the local values needed from one function. When you call another function, it creates another stack frame with the data for the next function, and it can keep doing this until you run out of RAM. And typically you're 10 or 20 layers deep in a normal program. You're in the operating system, then you call main, then you call a subroutine, it calls another subroutine, that calls printf, it calls some lower level function. You're typically many layers deep. All right, I got a few more eye clickers. It's not time for a break yet. We'll keep going. So where is the EIP? All right, quit at 25. All right, the EIP is a register. It's also part of the CPU, where the most specific answer is, best answer here is it's a register. And this is the most important register from the viewpoint of an attacker, because if you can control the EIP, you can redirect execution. Controlling other registers can often be used to achieve the same goal, but the most direct way to take over a machine is to get control of the EIP. Then point it to the instructions I put in there, and now I own the box. All right, stop that. All right, so where's the stack? I'll quit at 25. All right, it's in RAM. That's main memory. It's worth mentioning, by the way, that this discussion of where data can be stored on a computer is a little bit obsolete. The main memory is the RAM. The processor has registers for temporary storage, which are not anywhere in the RAM address. And another thing which modern computers have is a secure coprocessor. PCs have a trusted computing module, and iPhones have a secure element. And those are special chips that have more memory that is not anywhere in the address space of the main processor, so you can hide cryptographic keys in there, and no possible exploit can trick the processor into coughing up the key. It's not available to the processor. It has a second chip which can decrypt things with that key, so the main processor can use it, but there's no way any code in the main processor can access that key. Anyway, let's try this one. Where are the instructions for the CPU? All right, I'll quit at 30 here. All right, and that's going to be the code section. All right. And where are temporary things allocated with malloc? I'll quit at 30. All right, that's the heap. And Windows programs actually have a bunch of different heaps. It can get mighty confusing. All right. So these are assembly language instructions. You have a thing called the mnemonic, which in my opinion should have been called a verb, but they failed to ask me. And then you have operands. So this is move ECX 0x42. Now what this does is take the direct immediate value, 42, and put it in the register, ECX. 42 is in hexadecimal, that's what the 0x means, so instead of 4 tens plus 2, it's 4 16s plus 2. All right, the move ECX command is B9. The value 42 looks like this, 42, 0, 0, 0, 0, 0, 0, 1, 2, 3. That's too many right there, let me fix that. That's the problem with binary, it's easy to have too many. There. Because it's a 32-bit processor, and each 2 characters in hexadecimal is a byte, so it's 1, 2, 3, 4 bytes. And it's little endian, just to give us all headaches. So this is the number of 1s, this is the number of 256s, this is the number of 256 squared, and this is the number of 256 cubed. So the immediate value 42 has 6 bytes of 0, and so this in hex looks like this. B9 is moved into the ECX register, and the rest is the immediate value. So it takes 5 bytes of code to encode that instruction. All right. So here's an example. There's the format. You have move, you have destination, and then source. This is the Intel format. In the Intel format, the destination is on the left and the source is on the right. In AT&T, they're reversed. And each developer and each tool maker makes an apparently random decision which one to use. So you have to just sort of get used to figuring out which one by looking. And what I always do is look in the code for an immediate value like 42, because you can't put anything in a value like 42. That must be the source. Immediate values have to be there, going into some place like a register or a memory location. Anyway, like I mentioned, endian is an issue. A big endian would be the way you're normally used to writing things, where the numbers on the left are the highest value, and the ones on the right are the smallest value. But x86 uses little endian, so it's backwards. And that's the game. Network data goes on as big endian. So it's very easy to get network addresses backwards, and there's a lot of known bugs where network addresses are actually backwards in real equipment and sending things to meaningless IP addresses. But it's very easy to get it confused. So here's 127.0.0.1, would be sent over the network like that, but stored in RAM like that. This is just one of the many little headaches that we'll get to you. All right. So immediate operands are just fixed values like 1, 2, and 3 that are just numbers. Registers refer to these memory locations, so it'll be the 32-bit value stored in one of those registers, and you can have memory addresses. This means take the 32 bits of EAX, interpret that as an address, and go find that address in RAM. So this is how you would write to a block of RAM. You'd write to a register and then increment the register by 4 because it takes 4 bytes to store 32 bits. And the addresses count bytes, not words. So here's the registers. You have EAX, A, B, C, and D. You have the extended base pointer, the stack pointer, and the stack index. So I'm not sure what stack index or what it is. These things could all be used for any purpose, but in particular, the extended stack pointer typically points to the top of the stack. This usually points to the bottom of the stack, and this is usually used to count in a loop, in bytes, like if you're copying words. A, B, C, and D are used sort of interchangeably for temporary purposes, but typically if you return from a function, the return value is an EAX. Over here we have flags, which tell you things like whether the last operation was 0 or whether it was negative. And you have the EIP, a special one here with a special purpose. Like we said, that points to the next instruction to be processed. So if we are somehow able to gain control of the EIP, we're very close to gaining control of the box. If we can also inject code into an executable segment, then we can change the EIP to point to that code and own the box. Those are things that are not always possible, especially in modern operating systems like modern versions of Windows that have many defenses to try to stop these attacks. All right, so that's those things. There's also segment registers that track sections of memory. We'll see those go by occasionally. All right. For backward compatibility and special purposes, you can actually refer to things 16 bits or 8 bits at a time, the way you used to back in the old days on really old processors. So A low and A high are 8-bit registers, and there's also 16-bit registers available too. And there's occasionally reason to do that, although it's not that common. So there's EAX, AX, A high, and A low, referring to the whole 32-bit thing, the 16-bit portion, and the 2 8-bit portions inside there. So you can move just 8 bits at a time if you want to, but normally you prefer to move 32 bits at a time for speed. All right. So these things store data or memory addresses. They can be used for almost any purpose. There are a few special types of instructions that use them for a special purpose. Like there's now multiplication and division in the modern Intel processors. When I started, there was no multiplication or division. If you wanted those things, you had to code it out of addition and subtraction. Modern processors have multiplication and division, and if you do, you know how to use EAX and EDX to carry portions of the number. All right. Here's the flags. Set or cleared, each bit is a flag that indicates a condition, like the last operation overflowed and had a 1 carried over, so it was actually 33 bits of answer, or the last operation was 0, and things like that. There's the 0 flag, the carry flag, the sign flag tells you when the result of the last thing was negative, and the trap flag you can turn on, which causes your processor to only do 1 instruction at a time, which is something you'd use in a debugger. Anyway, there's the EIP. This is the address of the next instruction to be executed. So normally it just hops through your assembly code from one instruction to the next. As you've seen, that move instruction was 5 bytes, so the instructions are not all the same size. So the EIP doesn't just count 1, 2, 3. It counts skipping ahead by a few bytes, however many it has to get to the next instruction. And when you call a subroutine, it jumps to another whole area and tosses its instruction somewhere else, and then when it hits a return, it tries to come back and resume where it left off. And that's the vulnerable spot where you typically take over the machine, because you find a way to confuse it about how to return, and it returns to the wrong instruction. All right, so a few more eye clickers. The technical term for the NOP instruction. Go to 25. And that is a mnemonic. Stands for no operation. The NOP instruction does nothing except just sort of pad things out, and it's used by compilers to fill things up to say the next 32-bit word, and it's used by hackers to create a large region called the NOP sled, so that when you're trying to jump into your attack code, you can miss by some large region, and as long as you hit anywhere in the NOP sled, it will go NOP, 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 and then run your egg. So intrusion detection systems can look for things that contain a whole bunch of NOPs and block them as malware. Anyway. All right, so in what order are IP addresses sent over the network? If you look at them, say, in Wireshark, I'll quit at 25. All right, they're sent big endian, the same 127.0.0.1. The logical order is how network traffic is arranged. All right, I want to put 8 into EAX. What kind of data is 8? All right, I'll wait till 30. All right, that's an immediate value, just a plain number. That's what you call it. Good? All right. All right, what register determines which instruction will be processed next? I'll wait till 25. All right. All right, that's of course EIP, the extended instruction pointer. All right. And which register holds values like subtotals when you're doing calculations? I'll quit at 25. All right, those are the general purpose registers like EAX. The EA is in fact called the accumulator. In the original processors, in 8 bits, there was only one register called A to be the accumulator, and that came from mechanical adding machines before there were electronic computers where you'd type in dollar amounts on a cash register and press this big button chunk, and that would add it to the accumulator, and it would just continue to add money for each purchase until you got the total amount owed. And the earliest processors just imitated the mechanical calculators that were their predecessors. All right, and which one will tell you whether the last operation resulted in 0? This is how the assembly code actually handles something like a loop. Something is counting down. When it hits 0, it's time to leave the loop. All right, quit at 30. All right, and that's in one of the flags. One of the flags is the 0 flag. All right, good. So, just a little bit more of this, and then you can go do some projects. So, here's a few simple instructions. We're going to do a little more. Like I say, you're only learning a little assembly in this class. There's a very good assembly course you can take over in the other department if you really want to learn it, which is a good thing to learn. All right, so move is the simplest one. In the format we're using here, it's move source to destination. It turns out that there are hundreds of move instructions. Move immediate value to register, move register to register, move register to indirect register, so the register points to a memory location, move indirect register plus a number to register. Very boring variations on the same theme. Anyway, this is in tel format with destination first, and if you see brackets around a thing like EBX, that means take EBX as the address and go to that location in RAM. All right, so here's some examples. Move EAX, EBX. We'll put EBX into EAX. This next one, we'll put 42 in EAX. This one here, we'll go look up the memory location, 4037C4, and the 32 bits it finds there, it's going to put into EAX. This one here is going to take EBX, interpret it as an address, go look up that contents of memory, and put it in EAX. This is the kind of thing you'll see very often when you have a block of code moving a whole bunch of memory to another location in memory. I mentioned before, you have a location, EBX plus ESI times 4. That's going to refer to a location starting at EBX and counting this number of words up and move that word into EAX. And this is what you do when you process a whole block of memory. You pull 32 bits out, then you increment ESI and pull the next 32 bits out to do whatever you're doing. And you'll see that very often in code as some object is copied to another object. Like if you have a string variable copied to another string variable, it's going to be implemented as that instruction followed by something like increment ESI, and on it goes. And the loop, jumping back if ESI minus something is not 0 yet. All right, then there's load effective address. This is a way to calculate addresses. So this will put EBX plus 8, calculate it, and then take the address of it and put it in EAX. It is strange and convoluted, but the instruction you might like that would move the literal value EBX plus 8 into EAX doesn't exist. This is how you have to do it. You turn it into a memory address, interpret it as a memory address, and then calculate the effective address and put it in EAX. It's a little twisted and backwards, but that's one way to do math on registers. So here's an example of this. You have EBX is 340 here, and so you take EBX plus 8, which is down here, and you put that in EAX. That's what's going on. This is when you're doing indirectly. Okay. All right. Place the value from memory into EAX. Right. If you move EAX, this one here, if you move EAX, EBX plus 8, it will take the value here and put it in EAX, which is 20. If you have load effective address, it will take this value here, ending in 48, and put it in EAX. So it's worth knowing. All right, there's plenty of other operands like subtract, add, increment adds 1, decrement subtracts 1. You have multiply and divide, not that commonly used. And then NOP that does nothing, which turns out to be quite useful for attackers and not used very much otherwise, except that there are certain instructions that have to start on a 32-bit boundary, so you have to fill with 2 or 3 NOPs to get there. And then there's the stack. Like I say, last in and first out. The EBP points to the bottom of the current stack frame, and the ESP points to the top of the current stack frame. So all the temporary variables that one routine uses are between those 2 pointers. And when you return from the function, it moves the EBP down and ESP down because it's done using all that temporary stuff and works on a different stack frame. And when you call a subroutine, it increases EBP and ESP to create a new stack frame on top, which operates as long as you're in that function. And that's the process specifically designed to match the idea of structured programming, where you have little routines that do a job and you call the routines instead of having a long chain of spaghetti code that just has everything in it. You call subroutines, and that's what makes it vulnerable to most of the attacks, buffer overflows and such. And memory corruption errors in general come by exploiting this process by overrunning something in the stack and causing it to get confused about how to return. So you can do call or enter to enter a function, and when you're done, you can return with leave or ret, which will return back. And both of these cause the stack frame to change by creating a new stack frame if you're entering a subroutine, and by discarding it and moving to the previous stack frame if you're returning. So function calls have a prologue. At the start of a function, there's a series of about 6 or 8 machine language commands that will create the stack frame. So they change the value ESP and EBP to make enough room. And it calculates, the compiler decides how much room you need. If you have a string variable that's 100 bytes, then it will make sure you have 100 plus some more bytes there. And it sets aside enough room to work on the stack. Then when you're done with the function, it will undo that. Move back to the previous stack frame as it passes control back to the calling function. So here's the stack frame. Your main function might be here, then you call a subroutine that's here, then you call another subroutine. So if you're in main, then you call something like check password, and check password calls something like print, and now you're down here. And when you're done printing, you move ESP and EBP to recover to this frame, and when you're done checking the password, you return back up here. All right. That's the game of it. And that's how it looks. Each stack frame has a local variable stored on it, then it's got the old extended base pointer and the return address, which is the stored EIP, and that's the trick. If we manage to overrun one of these variables, we can write past where we're supposed to be and change this return address so that when it tries to return, it's got an invalid memory address, and that'll cause a denial of service, but if we're careful enough, we can give it a working memory address that points to code of our choice, and now we control the box.
In this case.
Yeah.
EBP is supposed to be at the end, right?
Yeah, I think it's supposed, I do think there's an error. I would say that the return address should be off the end of the stack frame. That's how I normally interpret it. Yeah, I agree with you. I think this has an error in this slide. All right, so test, we'll compare two things. Without altering them, so you can test EAX to EAX. That will always have a result of 0. Those two things are equal. You can compare them, and that will set the 0 flag if they are equal. The test will do the opposite. So 0 flag if EAX is 0. This will set 0 flag if the two numbers are equal. Anyway, I must say, I don't remember these details when I'm reading assembly code. I'm too wimpy. Well, you'll see the sleazy way. If you're not very good at assembler, you just look at like the names of the routines it's calling and the string constants and stuff, and you can sort of tell what's going on. But if you want to really follow it, then you have to get good at these little subtleties. So JZ will jump if the 0 flag is set, and JNZ will jump if the 0 flag is clear, whether the result of the last operation, which was probably something like a test or a compare, was 0 or not. So an if statement, if something is true, go here, turns into a compare followed by a JZ or a JNZ in assembler. So you have a main function. This is where all C programs start. This is where entry is. It always looks like this. You have main, and then you have argc and argv. Those are parameters that are passed into your main routine if you have it. And the first one counts the number of arguments on the command line, which has to be at least 1 because you have to run it with the name of the program, and that's 1. Then so you might have something like who am I, which is a command with no parameters. So it would have an argc of 1 and nothing in argv. Or you could have something like ping google.com. That's going to have 2 parameters, so argc would be 2, and the second, the pointer to the array of names containing the arguments would contain google.com. And if you have a series of things like copy food a bar, then you'd have a series of character strings over in argv. That's how main looks like. So there you are, copy food a bar. You have 3 arguments. The first one is CP, next one is foo, next one is bar. And everything in C always starts counting at 0, which gives everyone a headache and creates an entire class of bugs called off by 1 errors. It is very common that when you try to do something 10 times, you accidentally do it 9 or 11 times because nobody can keep this straight. There was a long dead language I learned in 1974 called BASIC, where you didn't do this. If you wanted to do something 10 times, you just said for I equals 1, 2, 10, do something and the next I. And nobody ever had off by 1 errors in these early primitive days. But for some ungodly reason, C did not do it that way. And everybody gets a headache from now on. Anyway, because if you have 3 things, of course you numbered them 0, 1, 2. That's how when I was a kid, we learned to count 3 things like 1, 2, and 3, but somehow that's not cool enough. Anyway, so here's the last batch of iClickers. All right. So what does that instruction do? Better wait a while. All right. I see a good answer. I look like you did too. I'll quit at 40. All right. That's B. A good popular answer. Glad to see it. So this is indirect addressing. So you take EBX, interpret it as an address, go find that memory in RAM, that location in RAM's contents, and put it in EAX. B. All right, good.
What's the difference between B and D?
What's that?
What's the difference between B
B and what?
and D?
And D. Because this would just put the contents of EBX in EAX. This puts the contents of what, like if EBX is 1,000, this would put 1,000 in EAX, but this would put the contents of memory location 1,000 in EAX. So they're quite different. This interprets EBX as a pointer. This interprets EBX as a literal value. Okay.
Brackets?
Brackets. Brackets are what makes it a pointer. Brackets mean memory location indicated by whatever's inside there. Exactly. Good. All right. How about this one? Which command will retrieve data from RAM? All right. Guess I can quit at 30. See the answers are in. All right, and that's C, which is just like the previous slide. B does not do it because this is load effective address. So it calculates this and then looks at the address, not the contents. It looks like it's referring to the contents of a memory location, but it's not. It's referring to the address of the memory location. So this will put whatever is the EDX plus 16 into ECX. This is the one that will actually fetch location from RAM and put it in EBX.
So B is not looking at the memory?
It's not. It's the strangest thing. You would think the logical thing to do here would be to just put it right here, EBX plus 16. The problem is you don't get that instruction. The designers of the microprocessor didn't give you that. So instead of giving you the obvious instruction that would make sense, you have to sort of do it backwards. You have to interpret it as an address, increment it, and then load the address into here. This amounts to the same thing, but that other instruction is just not one of your choices. If you get right down to the silicon, combination of not and gates, the way to wire them up, that's probably why it is this way. You know, you can't just have any instruction. Some of them are easy to make with the actual silicon devices that are available, and some of them are not easy to make. So that's what's actually happening that looks like capriciousness to the assembly language programmer.
Because one of the previous slide, I mean,
Yeah.
you had like in,
This one here,
no, this one of the previous slides.
Yeah.
You had like operations inside the brackets.
you can do that.
And moving a chunk of memory.
Yeah, if this was move,
Oh,
then it would do that. Then it would take the contents of RAM there and put it here. The fact that it's load effective address is what undoes that. It calculates this location and then puts the address here, not the contents. All right. Yeah, I find that to be one of the more confusing machine language commands. That one, and also I think test, gives me a headache. I often get it wrong. All right. All right, how about this one? Which one will change the size of the stack? All right, I'll quit at 30. Looks like the answers are in. All right, and that's push. Push adds data to stack, which makes it bigger. All the rest of these just move data around without changing the total amount of bytes on the stack. All right, which one is repeated many times in buffer overflow attacks? All right, I'll quit at 25. All right, that's NOP to make the NOP sled. All right. All right. Which one retrieves data from the stack? And these are not complete commands, just the mnemonic. Anyway, I'll quit at 30. All right, and that's pop. Push puts data on the stack, pop retrieves data from the stack and makes the stack smaller. And you follow it with some place to put it, like a memory location or a register. All right, so that's it for that. Let me stop the recording, which is 126, chapter 5, I think. I don't know. I'll figure